This is Lab 1, the queuing analysis lab. And oops, don't want to go jump ahead. Now we are on video 3, our final video for this lab, which is on Jackson networks. In video 1, we did MM1 queuing systems where we had a single capacity server, a single server with capacity 1, and we learned how to compute the performance metrics of utilization, number in system, and time in system. In the second video, we extended these results for MMC queuing system, where in this case C represents the capacity of the server, and so the solution, the example that we did in video 2, had a capacity 2 server. In the last video, video 3, we are interested in networks of queues. In particular, we're interested in something called a Jackson network, which we'll define a little bit more formally here in a little bit. But let's just assume that we have a system that looks as the following. We have 3 servers, S1, S2, and S3. And each one of these servers is similar to what we had seen before, where we have arriving entities, they receive service, and then they depart. The difference here is that we have the network representation, and for our example model, we're going to assume that 60% of the entities after being processed by server 1 go to server 2, and the remaining 40% go to server 3. Finally, after finishing processing at server 3, we're going to assume that 10% of the entities require reprocessing or go through what's called reentrancy. So 10%, some of the entities that go to 10% of the entities that go to server 3 will actually be reprocessed by server 3 a second or possibly third or fourth or fifth time. So we're going to make some assumptions here. We're going to assume that we have the same 96 entities per hour arrival rate that we saw in the previous example. We're going to assume that server S1 has a capacity of 2 and a service rate of 60, exactly what we saw before. For server 2, we're going to assume that it has capacity 1 and a mean service rate also of 60 per hour. And for server 3, we have capacity 1 and a mean service rate of 50 per hour. And our interest is exactly what it was before. We're interested in the utilization. In this case, we have 3 utilizations, one for server 1, server 2, and one for server 3. We're interested in the long-term average number of entities in the system, and we're interested in the time that entities spend in the system. In this case, we're, as opposed to our previous example where we're dealing with individual queuing systems, we have the network representation. So we are interested in how many entities are in the entire system, and similarly the time that those entities spend in the entire system, not within one little component of our system. So if our system is a Jackson network, which we will define more formally here in just a second, what that tells us is that we can decompose our system into its individual single server queuing systems, analyze those independently, and then aggregate the results together to get our system performance. So let's look at what we mean by that. So if we look at our just S1, we can see that we have an arrival rate of 96 per hour. We have capacity 2 server, we have a service rate of 60. And so if we think about this independently, we can assume that we have an MM2 queuing system. Again, this assumes that my arrivals are Poisson and my service times are exponentially distributed, which let's just assume they are for the time being. And now we can analyze this MM2 queuing system exactly how we did in the previous video. And when we did this previously, we got a utilization of 0.8. We got a number in the system of 4.444, and we got a time in system of 0.046. 0.046 hours, which is roughly 2.76 minutes. So this is exactly what we did in the previous video. Now, if we look at server 2 and server 3 and analyze those individually, then we see that the arrivals to server 2 and server 3 later on depend on the departures from server 1. And so if we look at server 2, let me get rid of these values here and just work on server 2 up here. What's the arrival rate that server 2 sees? The arrival rate that server 2 sees. Well, since server 1 is stable, meaning its utilization is strictly less than 1, we know that everything that departs or that arrives to server 1 also departs. So the service rate that server 2 sees is simply 60%, 0.6 times lambda 1. So it sees 60% of what server 1 saw. In our case, this is 0.6 times our 96, which is equal to 57.6. And so if we then analyze this system independently, we can assume that we now have an MM1 queuing system with lambda equal to 57.6, mu equal to 60, and c equal to 1. And so I'm going to jump over here rather than doing that by hand to just use our MMC program. MMC, and we have a 57.6 is our arrival rate, 60 is our service rate, 1 is our server, and so we can see that we expect 24 entities in the queue, and the timing system is 0.4167. So L2 ends up being 24, and W2 is 0.4167 hours, or 25 minutes. So if we treat these independently, everything that goes to S1 spends 2.76 minutes. Those that go to S2 spend an additional 25 minutes. So the entities that traverse from S1 to S2 spend roughly 27.76 minutes in the system. For server 3, we have this reentrant flow, and so that complicates things just a little bit. Not too much, but a little bit. So when we think about the arrival rate to S3, lambda 3, it's comprised of two components. It's comprised of the 40% of entities from that went to S1, plus those reentrant entities, or the entities that are sent back. So this is 10% of everything that entered lambda 3. And so we get 0.9 times lambda 3 is 0.4 times lambda 1. Lambda 3 is equal to approximately 42.667. And so now we have an MM1 queuing system with lambda 42.667, mu equal to 50. And so we have L3, W3, and we'll again use MMC to compute those. So we will have MMC of 42.667, 50, and 1. And so we have a number in system of 5.819 and time in system of 0.1364. So our number in system is 5.189. I'm sorry, 5.819. And W is 0.136 hours, which is approximately 8.184 minutes. And so now that we've decomposed our system into three individual systems, S1, S2, and S3, and analyze those independently, we can now aggregate the results. And so our overall L will simply be equal to L1 plus L2 plus L3, which is 4.444 right here, plus 5.819. I'm sorry, 24. I got my numbers mixed up. Plus 24, now plus 5.819. And the overall average number in system is 34.263. And so this tells us that on average there will be 34.263 entities in the system overall. When we think about W, all entities don't go to all stations because we have this probabilistic routing. Some go from S1 to S2, some go from S1 to S3. So we have to figure out how that's going to impact my overall time and system. One way I can do that is I can just use this weighted average. So I can say this is going to be W1 because all entities go to server 1 plus 60% W2 plus 40% W3. And so this gives me 2.7, let's do this in minutes, 2.76 minutes plus 60% times 25 minutes plus 40% of 8.184 minutes for an overall 21.034 minutes. Before we talk about the more formal definition of the Jackson network, I want to show an alternative way to compute W, or the time in system. The way we computed it for this model is relatively straightforward because we have a fairly simple flow. Everything goes to S1, some subset goes to S2, and the remainder go to S3, and so we have a pretty simplistic flow. In the general case, this might not be true. So what we can do instead is we can use Little's law to help us. Little's law, the form that I'm familiar with, L equals lambda W. And in particular, we're interested in solving for W. So W is equal to L over lambda. So what I'm going to do is I'm going to consider my system. If we think about an abstract view of our system like this, here's S1, S2, S3, everything comes in here and things leave here, and we have some reentrancy here. I'm going to think about this system by just sort of drawing a box around our system. And I'm going to apply Little's law to our outer system, right? Because we know the lambda to our outer system is 96, and now we know the L value, right? We just computed the L value. The L value is 34.263. 34.263. And so Little's law tells us that the corresponding W will be 34.263 divided by 96, which is 0.357 hours, which is 21.42 minutes. So it's slightly different. We have 21.42. We computed 21.034. The difference that we have is just in the round off error on how we did the calculation. And so the nice part about using Little's law to compute W is that it works for an arbitrarily complex interior network. So no matter how much reentrancy I have, no matter how many stations I have, I can always apply Little's law by simply drawing a box around the entire system and using the system overall to compute the time and system values. So what we end up doing, oops, don't want to go there, is, as I mentioned earlier, with the Jackson network, what we do is we disaggregate our system. So we divide our system up into, here's a subsystem, here's a subsystem, oops, keep hitting my page forward, here's a subsystem, then here's a subsystem, and analyzing these independently and then aggregating the results. You can only do this under certain assumptions, and the definition of a Jackson network really has 5 conditions. The first one is that external arrivals have to be exponential, so the exponential inter-arrival time. And we see we meet that condition here because we only have one set of external arrivals. All of the internal processing times also have to be exponential. And what that does is it ensures if I have exponential arrivals, if we consider S1 for example, if I have exponential inter-arrival times and I have exponential service times, then my inter-departure times, that departure times that the departure process will also be exponential. Because that departure process from S1 is exponential, then the arrival process that S2 and S3 will also be exponential if the decision of S2 or S3 is probabilistic. In other words, if I have a probabilistic routing between S1 and S2 or S1 and S3. And so that's the third condition, that we have probabilistic routing. The fourth condition is that all of the internal queues are infinite, which we need for an MMC queuing system anyway. And the final condition for validity or for feasibility is that all of the individual rows, all of the individual utilizations have to be strictly less than 1. And you can think about, for example, if this utilization of S1 were greater than 1, that would tell us that you would have an infinite number at steady state, and so we can't have that for a feasible system. And so, in summary, our 5 conditions for a Jackson network are the external arrivals all have to be exponential or exponentially distributed inter-arrival times, Poisson arrivals. All of the internal processing times have to be exponentially distributed. All of the routing inside has to be probabilistic. We have to have infinite queues in front of each server, and when we separate the system or divide the system up, all of the individually computed rows have to be strictly less than 1. And if these 5 conditions hold, then we can simply analyze the subsystems independently, aggregate the results, and get the overall system results. And so this is a very nice analysis tool that we have to analyze these networks of queues, which we will see for the remainder of the semester.